Hello and welcome to today's class. Today we'll be looking at Real Analysis 1. Therefore, before we continue, my name is Dr. Wanjala Titus, and today I'll be taking you through introductory part of the Real Analysis. If you haven't subscribed into my channel, take your time, subscribe so that in case of any information, you'll be the first one to be notified. Thank you. Let's continue. Under the Real Analysis 1, in the introductory part, we are going to look at the set theory and the real number system. But we'll look at what is a set. A set is a well-defined collection of distinct objects. And what are these objects? These objects are called elements or the members of the set. Now, we have to look at the set notation. Under set notation, we all know that sets are typically denoted by capital letters. Denoted by capital letters. Any set is always denoted by capital letters. E.g., we have X, Y, A, B. Those are our sets. And then, what are now the elements? The elements of a set are always denoted by small or lowercase letters. The lowercase letters. Elements by lowercase letters. E.g., we have this one will be X, it will be Y, then we have A and B. Those are now the elements. Then we'll therefore let this symbol that we are going to use. The symbol that we normally use in the set notation is this one. This one means the element of an element of then when you see this one is not an element of. That's now how we can use the symbol in the set notation. Let us look at the set representation. Under set representation, we are going to look at two ways of representing sets. Number one method is roster method. Under the roster method, this says listing of all elements. All elements. Are we getting? E.g., for example, we can say a set A is given by 2, 4, 6, 8. This is now our set. But we can also still represent sets by using letters, lowercase letters, which are the elements. We can say it will be A, E, O, and U. We're getting. That's now the roster method. As we proceed, we will have the set builder notation. notation, the set builder notation. This is our second way of representation of set. In this, we will say we use a property that all elements satisfy. Use a property that all elements satisfy. For example, we can have a set A with as an element x of x. This one will be a positive integer. This one is a positive integer, which is less than 5. You can have a set B of x, which is like as a vowel in English alphabet. From this one, are we getting? So in reaching there, we will therefore look at this thing called the set operations. Set operations. Under the set operation, we are going to look at 4 ways of operation of sets. Number 1 is union. And the union, in the union, for example, a union is represented by U, like a union of A and B is a set of all elements, that are in A, and B. When you find a question asking you to find the union, those are elements that are both in A and B. For example, if we have a set A being represented by 2, 4, 6, and B as 5, 7, 8. Are we getting? So A union B, it will be a set of all elements. You rearrange them by saying 2, 4, 6. We start by having 5 first. 5, 6, 7, and 8. That's how we calculate a union. Are we there? So in reaching there, we are going to look at the intersection. Under the intersection, these are set. Intersection is the set of elements that are in A, elements that are in A, a set of elements that are in A and in B, and in B. So, for example, we have a question. A set A is equals to 1, 2, 3, and B as 3, 4, 5. We come to this conclusion that we say that a set of elements, that the elements that are only found in A and at the same time found in B, that's the intersection. We will have our answer as A intersection B being equals to 3. Why? 3 is found in both A and B. Then the third one, we are going to look at the complement. The complement is always represented by something like a prime. Like, for example, let us say a prime. That's now a complement. But in some cases, you'll find others saying a complement. It's still the same. So, a complement is the set of all elements, that are in A, are in A, but not in B. Not in B. These are a set of all elements that are in A, but not in B. For example, we have a question giving us that if a set a complement is a set of all elements that are in the universal set that are not in A, that are not in A. A complement is a set of elements that are in the universal set that are not in A. For example, we have our universal set as 1, 2, 3, 4, and 5. Then at the same time, we have our A, set A as 1, 2, 3. Yeah, let's switch from there. 1, 2, 3. So we say our A complement, our answer now will be a set of all elements that are in the universal set but not in A. So we check what is not here, not in here. They are here but are not here. That is the answer. So we say our answer, we will check 1 is here, both sides we cannot pick it. 2 is there, we cannot pick it. 3 is there, we cannot pick it. So our answer is going to be 4, 5. That's how to calculate the complement. The last operation will